We're going to look at a few cautions about the p-value to avoid some common misinterpretations. One of those is the relationship between the sample size and the amount of significance we get, or the p-value. So looking at an example here involving coin tosses where we're counting heads, our question is whether we have a fair coin. So if the coin is fair, we'll get heads 50% of the time. If the coin is unfair, we expect to get heads something other than 50% of the time. Now in our first sample, we get 56 heads out of 100 tosses. So that's 56 out of 100. This is a sample proportion, so we'll call it p hat. And that comes out to 0.56. This is with a sample size of n equals 100. In our second study, we got 560 heads out of 1,000 tosses. So that's 560 out of 1,000. This is still p hat equals 0.56. It's the exact same proportion. But now we have 1,000 trials. So what we're going to investigate, first we'll just take our guess based on what we've learned so far and what our intuition is. If we get p hat equals 0.56 in both cases, do they both present the same amount of evidence that this coin is not fair? Well, with 100 and 1,000, maybe your intuition isn't really strong, but if you imagine a very small sample like 4 coin tosses versus a very large sample like 1,000,000 coin tosses, intuitively you might expect the 1,000,000 coin tosses to be a little bit more reliable than the 4 coin tosses, in which we really only have a pretty limited set of possible outcomes there. Even if all 4 of them came up heads, it wouldn't be all that surprising. It would just be slightly unusual. So, intuitively, we might expect that the second study gives us stronger evidence just based on that kind of thinking. Let's look at our randomization dot plots in order to solidify that a little bit more. Marking our sample statistic on this horizontal axis here, this is where we find p hat equals 0.56. It's between 0.54 and 0.6, a little closer to 0.54. Now I'm going to put in a vertical line going up from there. And you may or may not find that this line of dots here is to the right of your line on the n equals 100. And it's really not important whether those dots are included or not. I think the point is made pretty well either way. For n equals 100, I'm going to assume that all of these dots are counted as being more extreme than my sample statistic. So counting up those dots, I get 21. Whereas looking down here at n equals 1,000, I can see that more extreme than 0.56 over here, I get no dots. The reason we're seeing this difference come up so profoundly is because when we have a smaller value of n, if we recall from our sampling distributions, when we have a smaller value of n over which we're calculating each sample statistic, we get a larger standard error, or more spread out. Our distribution is more spread out, which is like having a larger standard error. Remember, the standard error is really just the standard deviation of this distribution if the distribution represents a sample statistic. Down here we have a larger value of n, and where we get a larger value of n, we get a distribution that's more concentrated at the center, and more concentrated at the center means a smaller standard error. So to calculate the p-values based on these numbers of dots, Note that each of these distributions shows 100 randomization samples, so that's the number of dots in each distribution. We need that in order to calculate the proportion. The p-value for the test using n equals 100, well, 21 over the 100 randomization samples is 0.21. But we need to double that because this is actually a two-sided alternative hypothesis. So we get a p-value of 0.42. For the other test, we have 0 out of 100 randomization samples, which is 0.00. When we double that, it's still 0. So very dramatically different p-values we get from both of these tests, even though they both gave the same sample statistic of 0.56. So that intuition about the million tests versus 4 tests giving us stronger significance is really true mathematically. It really does hold true when we apply all the principles. So the reason these p-values are so different is that if the null hypothesis is actually false, we're much more likely to detect it with a large sample than we are with a small sample. And the reason for that is the much smaller standard error and the much more concentrated distribution that we get. We can see from this picture here how that more concentrated distribution does create smaller tails. If the alternative hypothesis is not true, then it doesn't necessarily mean that it's going to be more likely to get significance. What will tend to happen is if the alternative hypothesis is not true and the null hypothesis is true, then as your sample gets larger, you're going to see your sample statistic drift closer to that null value. So it's not necessarily a freebie that we're going to get significance. It just means that if there is a difference, it's much easier to detect it with a large sample than with a small sample.